Hello, welcome to lesson 12 on the Poisson distribution. The Poisson distribution is a discrete distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space. If these events occur with a known constant mean rate and independently of the time since the last event, then we have a Poisson distribution. So, some examples: the number of customers entering a store, the number of views of a web page. Those would be examples of real life situation that could be modeled with a Poisson distribution. The probability mass function of a Poisson random variable is as follows. The probability that x is equal to x is equal to e to the minus lambda times lambda to the x over x factorial for x equals 0, 1, 2, 3, 4. It's 0 otherwise. Lambda is the mean rate. And the E symbol, E is the irrational number. It's approximately 2.7. E is an irrational number, approximately 2.718. So one way to view the Poisson distribution is a special case of a binomial. N trials, probability of success, P. So this is the binomial PMF here, and we're going to show how we can use this to arrive at the PMF for the Poisson. So again, we're calling lambda the mean. The mean of a binomial is NP. Solving for P, we get lambda over N. So replacing P with the lambda over N, remember Q is equal to 1 minus P. So we get N choose X. Instead of P to the X, we get lambda over N to the X. Instead of 1 minus P or Q to the N minus X, we get 1 minus lambda over N to the power N minus X. Let me just write that in here. So Q, remember Q is equal to 1 minus P. Okay. Now, for n large and p small, so that product n times p lambda is not too big or small, that it's moderate, then this relationship will hold that the Poisson distribution is a special limiting case of a binomial. All right, so n choose x is n factorial over x factorial times n minus x factorial. Lambda over n to the x power, we can apply the x to the numerator and denominator. Lambda to the x over n to the x. Now we have here 1 minus lambda over n to the n minus x. So a subtraction of powers comes from division. So we can view an expression to the n minus x power is the same as writing that as the expression to the n divided by the expression to the x. Let me just make a little note there. So if you have a situation where you have something of the form, let's say, let me use t to the power n minus x. That's the same as t to the n divided by t to the x. All right, sorry about that. Let's just line that up again. So again, this last piece here, power n minus x, it's the same as the expression to the power n divided by the power x. All right, so we can cancel out. We have n factorial over n minus x factorial. So everything higher than n minus x will survive. Anything n minus x or lower will cancel out. So what's left here in the numerator So n factorial is n times n minus 1, n minus 2, all the way up to n minus x plus 1. Anything beyond that will cancel out with the n minus x factorial on the bottom. So we're left with n minus 1, n minus 2, up to n minus x plus 1. Now, downstairs here, we have n to the x. So we move that in front, and then we move the x factorial over to the second term. And there was no change on the last expression. Now, n to the x just means multiplying n out x times, and there are x terms in the numerator, because we have 1, 2, 3, up to this would be x minus 1, plus this extra term here, n. Now, we're going to look at what happens on this expression as n goes to infinity. So what's happening here? N over n goes to 1, n minus 1 over n goes to 1, n minus 2 over n goes to 1. A little bit trickier argument here, but essentially, again, not a rigorous proof, but essentially this entire expression, each of those fractions is going to approach 1. So that part's going to go to 1. The second piece here is not affected by n. And then the last fraction, again, a little bit tricky here. Notice we have a little bit different situation. In the numerator, the exponent is n. Denominator exponent is x. When you have a constant exponent, n is going to infinity, but x is a constant exponent. When you have a constant exponent, we can do the inside first. 1 minus a constant over infinity goes to 0. This is 1 to a fixed x power, so the denominator goes to 1. But the numerator, we have a situation where the base expression is going to 1, but the power is going to infinity. So that is a form of L'Hopital's rule. And I'm not going to do that out here, but this expression does have a limit of e to the minus lambda. So let me just give you that limit definition of e here. Sorry. So limit definition of e, 1 plus 1 over n to the power n. As n goes to infinity, that approaches e to the first power. So what's happening here is that instead of a 1 there, we have a negative lambda situation, and that's how we get the e to the minus lambda. But you would have to use L'Hopital's rule or some other technique there to prove that the limit in this numerator does go to e to the minus lambda. And so once you have all that, that gives us the probability mass function. The probability that x is equal to x is e to the minus lambda times lambda to the x over x factorial for x equals 0, 1, 2, 3, and so on. So that was the original PMF. And now we'll justify that it satisfies the conditions of a PMF, that all the terms are greater than or equal to 0, and the sum of the probabilities, the sum is 1. Now, e is a positive number. Raised to any power is positive. Lambda here is lambda is a constant raised to a power of the form 0, 1, 2, 3. So as long as lambda is positive, then this expression should stay positive. Yeah, so lambda is the mean rate of occurrences, so lambda cannot be a negative expression, so this expression will always be positive. Now, showing the sum is 1 is a little bit trickier. So we're going to need the power series for the exponential function from Calculus 2. Power series for e to the x or e to the t is summation and goes from 0 to infinity, t to the n over n factorial. So we're going to need that here. So this this sum that we're trying to show is 1 here. The expression that's changing, the index is x. So e to the minus lambda is a constant. So we can factor out e to the minus lambda. We can pull that in front, and then you want to convince yourself that this expression here is the series representation for E. Again, we have a lambda instead of a t, an x instead of an n, but it's the same format. It's the same format here. So this expression is the power series for e to the lambda. And so we get e to the minus lambda times e to the lambda, which is e to the 0, which is 1, which is what we wanted to show. All right, up next is the expected value of a Poisson random variable. Expected value is the mean. So we're doing the definition here, summation x times p of x. So we have x times our probability mass function, e to the minus lambda times lambda to the x over x factorial. Now, when x is 0, this expression is 0. So we can start at 1 and we can cancel out the x. So we can cancel out the x here. X factorial is x times x minus 1, x minus 2, and so on, or x times x minus 1 factorial. Cancel out the x's. Now, e to the minus lambda is constant. X is changing, so we can factor out e to the minus lambda. So now we almost have it in the right format here. We almost have it in the format of the series for a power series for E. We need this exponent to match the denominator term. Right? In the series for E, we need this exponent expression and the factorial on the bottom to be the same expression. So we're going to line that up by breaking down lambda to the x. We're going to break it apart, lambda to the first and lambda to the x minus 1. So that will total back to lambda to the x. The lambda in front we can factor out. That's a fixed constant in this sum. And then the remaining part is the E series, and that is e to the lambda. So this part here is e to the lambda. So we have lambda pulled out in front, e to the minus lambda pulled out in front, and then this series is by the form of the E power series. That is e to the minus, that's e to the lambda. So this product is e to the 0 is 1, and we're left with lambda. So the mean or expected value of the Poisson distribution is lambda. Now the variance here is a little tricky because if we try to multiply by x squared, we don't get a clean cancellation. There's only one copy of x in x factorial. So we're going to use a slightly different form here. It's possible to work with x squared, but it's a little bit messier. So instead of working with the expected value of x squared directly here, it's a little easier to do the expected value of x times x minus 1 because that cancels out better with the factorial expression. So we have to use a little bit of forward thinking here in terms of what's going to cancel out with x factorial. Now we can start this sum at 2 because if x is 0 or 1, these terms are 0. And so we can expand out the x factorial, x times x minus 1, x minus 2 factorial. We get the x and x minus 1 to cancel out. That was the whole point of using the slightly modified form here. We get the cancellation. So we get the cancellation here. The x's cancel out. The x minus 1s cancel out. And we're left with e to the minus lambda, lambda to the x over x minus 2 factorial. So similar to what we did before, we can factor out e to the minus lambda. We can break apart lambda to the x as lambda squared and x minus 2. So it matches the term on the bottom. And then we use the power series for e, and that expression is again e to the lambda. So this whole expected value is either the minus lambda times lambda squared, either the minus lambda times either the lambda is either the 0 is 1, that cancels out. So we get lambda squared after all that. So all that process gave us that the expected value of x times x minus 1 is lambda squared. Now we have to do a little extra work because we have to get the formula now for the variance. So we know that the expected value of x times x minus 1 is lambda squared. Multiplying that through, we get expected value of x squared minus x. Now, the expected value we can apply to each term individually. It's expected value of x squared minus e of x, and that is equal to lambda squared. Now, we calculated that e of x is lambda. So we know that e of x is lambda here. So we can plug that in. So expected value of x squared minus expected value of x is lambda squared. We know e of x is lambda, so we finally have e of x squared is lambda squared plus lambda. So plugging into the formula for variance, we get lambda squared plus lambda minus e of x squared minus lambda squared. That cancels out, and we finally get the variance is lambda, and the standard deviation is root lambda. So again, this is a lot of technical detail. The vast majority of the questions we have will be on using these things and not the proofs. The standard deviation is root lambda. Now, I'm not going to go through this in detail. It's possible to do the e of x squared directly, but the cancellation doesn't work out, and you have to do some extra steps here of subtracting and adding 1 to get the cancellation to work. So I think this method of doing e of x times x minus 1 is a little bit cleaner, but this will work here. You have to subtract and add 1, and it will work out to get e of x squared, and you end up in the same spot. Okay, this handles the theoretical portion of lesson 12. In the next video, we'll do some examples.